in its current form utilizes primarily secure multi-party computations as this cryptographic primitive that allows for those operations over encrypted state. And as the name implies, those kind of computations require multiple parties. So what we are building with Arcium is a decentralized confidential computing network. And inside of this DCZ network, I guess, that's a term we are trying to coin, I guess, decentralized confidential computing. In this network, nodes can just register just as in any other permissionless network, and can offer their compute resources essentially to perform those confidential operations. And then they find other peers and form clusters. So this entire network essentially gets permutated into clusters, and those clusters then can have different sizes, can have different trust assumptions, and they then run confidential computations. And our approach essentially is that we're building a stateless confidential computing network that uses existing blockchains as consensus layers and allows for confidential operations to be sort of executed from those blockchains. So confidential computations can now be part of smart contracts, and they get scheduled essentially as computations asynchronously, will be executed in our network and then settled back to the corresponding chain and smart contract. And that would be this high level overview of what we're trying to achieve with Arcium. Now, this concept of being able to run confidential computations over encrypted state, is sort of, if you hear it the first time, difficult to grasp principle, right? How can someone perform a computation over data without seeing that data and the output being correct, right? So there's multiple aspects to this, and also multiple aspects how the technology that we're building relates to what you mentioned, FHE, for example. Um, the two main parameters that we care about and why we chose our technological approach really are performance and trustlessness. That's the two things that matter in this context, right? So I personally think that if one builds encryption and privacy, confidentiality technology, and using that technology comes with an enormous performance latency penalty. There will be no use of that technology, and applications, companies, organizations will just opt to use the most efficient solution. And I think that's problematic, because the technology that we're building at the end of the day, for one, allows for enterprises and organizations to maintain privacy, but more importantly, I think every aspect of privacy will always boil down to the individual, right? And so enhancing technologies really are a way, I guess, to not land in a dystopia, to allow freedom and individuals' privacy. So I think we need to make it as compelling as possible to use these kinds of technologies. And one factor for this is those technologies need to be very efficient, close enough in efficiency to plain text execution.
Right. And that was the thing. Sorry to interrupt. That was,
Yeah,
I
no,
think, one of the main points about FHE is that currently it's about 1,000 times slower than plain text computation, which only really makes it feasible on niche protocols, not at large scale, at least not for now. So one thing that I want to understand from you is your way of doing this. How much more efficient is it compared to that? But I also meant to ask you, um, how did you get into this? Like, how, what's your journey been like to end up in the field of decentralized encrypted computation? I feel that's a pretty cool story there.
All right. So, in regards to the first question, um, you're right. Fully homomorphic encryption comes with this enormous computational overhead. And in some cases, that can be 1,000 times slowdown. But depending really on the kinds of operations, it can even be many more orders of magnitude slower. So that's a problem that needs to be addressed. And the technology that we're using is very similar actually to FHE on a certain level, right? The technology we're using, MPC, multi-party computations, um, in our case, I guess, with the protocols that we're building, utilizes a so-called pre-processing model. So the computation is being split into two phases: a pre-processing phase and an online phase. And the pre-processing phase is something that happens independent of the computational inputs and algorithms that should be executed. That just needs to be executed in order to generate so-called correlated randomness. So you will understand in a second what correlated randomness means. It's actually on a high level quite simple to understand. But what's important to realize about fully homomorphic encryption and the difficulties with that is that everything boils down to two core operations you're performing: additions and multiplications. And additions can be performed quite easily homomorphically, and homomorphically means to be able to have some value that is encrypted, that is in some encrypted representation, and you apply an operation of it, and it remains in this encrypted representation, right? So there's this homomorphism. So for additions, that's quite it's possible to realize that efficiently. Now for multiplications, a problem that arises with FHE essentially is so-called noise accumulation. So repeated executions of multiplications introduce noise to the ciphertext, and then a so-called bootstrapping protocol is required to reduce that noise. And that's really the center of where this inefficiency comes from. Um, and with those two basic operations, additions and multiplications, you can build all kinds of computations that you want as core building blocks. Now, to shift to the technology that we are using, we utilize something called somewhat homomorphic encryption, where we only care about the additions to be performed in this efficient homomorphic fashion. And for multiplications, we utilize this so-called correlated randomness that with this pre-processing model is to be assumed to have been generated in the past by the corresponding parties. And then this correlated randomness, which essentially can be seen as a multiplication that has been performed in the past, and then you using the factors and the product of that multiplication, and adjust it to some secret values that you now want to compute over, and correct the final output, right? So you do some heavy lifting in the past, and now you're able to do it efficiently. So that's the one of the core principles. And how multi-party computations work is multiple players in a computation holding so-called secret shares, and then them running local operations, like for example additions, and then running multiplications, where a bit of communication is required between those players. And then at the end, in order to construct the final output, um, combining those resulting secret shares back together in order to form some output. So, um, yeah, I think that would be a brief summary of MPC and FHE in relation. And what this allows is for very efficient online phase execution. So that comes very close to the plain text execution, depending
Okay.
on the protocol being used. So there's different kinds of protocols that can be used based on the trust assumptions that you're willing to take. Based on the trust assumptions, one can have against those peers, or those peers in the computation can have against each other. And so there's basically two concepts: honest majority, if you will, right? So more than half of participants in some computation behaving honestly. That could be the trust assumption against confidentiality, against the privacy of the data. But there's also a far better trust assumption, which would be dishonest majority. So, for example, one honest player. So if you have an arbitrarily large set of players in a computation, you would require that one of those players is not
Right.
maliciously playing together with the others to undermine the protocol. And that's really what we are working with this trust assumption, and then allowing anyone to sort of become an honest player, to join and um, on their own behave honestly, especially if they're executing a computation they care about. They can just run a node and behave honestly, and then have zero trust essentially.
Right. So going back to the bottom line of the performance for your semi-homomorphic encryption is that it's almost as fast as plain text. And what you're doing is you're using the MPC protocol to split this computation across the different nodes, the different validators that would then compute this, orchestrate the output back together, and then present the output to the end user. Um, with that process, I'm guessing, and this is kind of going into governance, right? You've mentioned that you are using a this what was it you called it,
Dishonest majority.
dishonest majority. So does that assume that there's only a limited number of trusted nodes, or what is the governance paradigm there?
So the paradigm would really be, for any given set of n nodes, um, there is one honest node. That's the trust assumption you would be running with, right?
Right.
And so if you have a traditional blockchain with practical Byzantine fault tolerance, your trust assumption essentially is more than half of nodes in this
Mm.
network form a correct consensus, right? Or it's you only you trusted 60% are honest, or 67%, something like that, right? Those are common systems, and for us,
Hmm.
it's the lowest possible trust assumption you can have in a distributed setting, right? One single participant should play according to protocol in order for this confidentiality to hold, right? And so that's the lowest possible trust assumption, but it can be brought to even zero, relatively speaking, because if
Right.
I'm part of a computation, I'm convinced that I'm honest, right? So for me, there would be zero trust, and then for others, there could be trust. They would have to trust that in a set there's one honest player. But what's so beautiful about using MPC with blockchains is that we can add transparency to the behavior of nodes, right? We can reduce trust by adding additionally to that accountability to their behavior. That's really what why MPC and blockchains is such a match made in heaven. So what we've added, so
I was I'm laughing because I was literally thinking about the same term, and it was funny to hear you say
yeah,
"match made in
nice.
heaven." I had that in my head.
Um, that's because it is. Yeah. um, no, what we have added as a paradigm, I think, is um, a new censorship resistance mechanism as well. Because um, what you can do with Arcium is you can create a so-called MXE MPC execution environment, which sort of can be seen as a trustless cryptography based confidential execution environment as an alternative to hardware-based trusted execution environments. Um, and for those, you assign computation clusters. But now um, we have this ideal trust assumption, which is great. But at the same time, those scientific papers circling around those systems with those very low trust assumptions have one fatal practical flaw, you could say, that on at the same time they enable one malicious player to DDoS the computation, because the default security assumption would be if someone misbehaves, the computation just fails because they can identify that,
Right.
but they can't identify why it failed specifically or what party caused that. And so that's a very problematic setup when being in the distributed setting, right? So if you have some application that really depends on those confidential operations to be executed, um, you can't have this this high risk of DDoS attacks for those executions, right? And so um, the way we were able to prevent those attacks is by adding so-called cheater identification. So this protocol is now, in our case, able to, if a failure occurs, to identify cryptographically what party caused it. And now, by
That's
combining
very
then
cool.
that with a blockchain system, we can have a collateral and slashing mechanism for this kind of misbehavior. And so we can have these clusters of nodes with this dishonest majority trust assumption that run computations. And if someone misbehaves, a proof is being generated and they get punished. So with that, we can introduce this sort of notion of guaranteed execution within those clusters.
Right. That's very cool. That must have a lot of use cases there. That's very interesting and probably unique application that I haven't really heard before. That's fantastic. So let me take you back to how you actually got to this point. Because obviously you have a wealth of knowledge into cryptography, blockchain, and computing. So I just want to understand a little bit about you and how you got into this industry and into this role.
So originally, I guess my journey begins when teaching myself programming at an early age, through building mods for video games, and then after high school, for some reason, against my parents, friends, and everyone's advice, I guess, I decided to go and study law. And although everyone was suggesting go study math, computer science, physics, I just wanted to study law because I felt like I already taught myself programming, and now I wanted to do something new. So I did that for a few years, and remained loyal to my passion of technology and programming, and did a lot of legal tech stuff. And funnily enough, during a small legal tech conference, got in contact with Ethereum. So I met a lawyer there that was building quite early smart contracts for banking applications. And this lawyer also had this tech background and was just teaching a bit of smart contract development, and was sending everyone some testnet tokens in order to play around. And so that was my earliest touching point. And then sometime later, COVID hit, and I had some free lecture free spare time during my law studies, and just had a simple idea for an application that I just developed for myself, essentially, because it solved an issue that I at this time had with using my iPad Pro as a professional working device. And I programmed that app, published it to the App Store, and it became this sort of overnight success. And that made it quite easy for me to then, after I guess 6 more months of criminal law, to pivot towards studying math and computer science. And yeah,
That's very
during
cool.
during studying math and computer science, we had a cryptography course, and that's where I met a few of my co-founders. And yeah, all of us had this interest in blockchain, and then just all of it started.
That's a cool story. What app did you build? What was the name of the app, and what did it do? What does it do?
Shift Screen is the name of the app, and it allowed you to connect your iPad and iPhone to an external monitor, and then be able to um, use it as a true secondary screen. Because at the time, all that Apple was supporting was mirroring the screen one to one onto this
Right.
monitor, and so not even the aspect ratio would fit. And with this app, you could have some freely floating windows on a secondary screen, and that was a big use case during COVID, and it really felt great to build this application, publish it to the App Store, and then have people from all over the world, right? Tens of thousands of people just actively using this small thing that I just developed for myself, essentially. Yeah, and having a better life with that application. So I think that was really an important moment, and I think I was, well, 19 years old. I think I was when I was doing that. So that was, I think it was really, yeah, I think it was a very important moment, which then allowed me to realize, okay, that's what I want to do. I want to build technology that solves issues. Yeah.
Right. That's super cool. So did you do any marketing for it, or did you just put it up on the App Store and people just found the app?
So I was cold emailing and DMing productivity and app influencers, and some medium-sized ones with a couple tens of thousands of followers started just doing videos on it without wanting a single penny from me. And that just got the ball rolling, and yeah, I wasn't required to spend a single cent on marketing. Funnily enough, it was just people doing videos about the app
That's
organically.
very cool.
That was crazy. Yeah.
Was the app free to use?
One-time purchase, $10.
That's super cool, man. Congratulations. That's awesome. That's an awesome backstory there. So then after that, you've moved into Arcium. You've thought about Arcium. I'm guessing, along with your co-founders, architected the idea, and you've also recently secured an investment from some big crypto investors. Congratulations, by the way. That's fantastic.
Oh, thank you so much. So it for Arcium itself, it's also really a story of development. So we originally started known as Elusive, and what
Hmm.
we originally sought out to do was to solve this issue of on-chain transactional privacy, because by default everything happens transparently on the ledger, and that limits really the ability for blockchains to scale into retail, and to scale to large applications that can replace the current Web 2 technologies we are using, because we are really used to a relatively high level of privacy in our everyday lives, right? Although it might not be perfect privacy, just having Google just giving Google access to our data, right, is different from giving the entire world access to our data, because now it's on a public ledger. And so what we were using back in the day was zero knowledge proofs, of course, as this perfect primitive for these kinds of applications. At the same time, we developed a very, very innovative, I really think, protocol to solve an issue that arises with zero knowledge proof based
Okay.
on-chain privacy compliance. Yeah, and
Right. Yeah, of
that's
course.
and so our direction was, okay. We want to support privacy, and don't want any centralization. But still, we require compliance, and I think um, that's also a different take that some other players have had, especially looking at failures in regards to compliance. But I think there is some reason in our societies why we wouldn't want bad actors to, for example, have this completely anonymous ability to move assets however they like. So um, the solution for this problem for us was using confidential computing with MPC, and essentially what we're building right now, um, and using those confidential computations to privately and securely screen transactions, encrypted transactions. And then, if they found some actor, let's say 1 week after a transaction has occurred, to be a bad actor, this network could screen the transactions and identify those performed by this bad actor, not revealing any information about all normal users, but revealing the activities of the bad actor. And with this setup of being able to screen those computations after they have occurred, it was also possible to introduce a decentralized consensus mechanism, right, with high consensus bounds, in order to have a correct decision making process. And so it was very innovative on that front, this protocol. But when developing it, we realized, and especially building this cheater identification system and doing all of this research and engineering work, that just limiting this ability to run computations over sensitive encrypted data, and most importantly, also be able to disclose information about it, right? So it's not just encrypted data to encrypted data, but in this case, it was revealed that an illicit actor has done something. So selective disclosure is so incredibly powerful, and would
Right.
have just been limited to the single use case, which I would argue, comparatively speaking to what's now possible, is quite boring, because I mean compliance is not the most interesting subject. So that's really the story of Arcium, evolving step by step, now into this dedicated network, fully focused on building this highly efficient yet trustless confidential computing technology.
Right. That's very cool. And I love the fact that you can determine what a bad actor might be after the transaction has taken place. How do you manage that? And what do you actually look for? Are you looking for, are you scanning for like wallet activity? And are you trying to associate the wallet with transactions on the chain? Like, how does that
So
work?
so again, we're not doing that anymore. That's something that we were planning on doing in the past and building the tech, and
Right.
then we said, okay, let's fully focus on just building confidential computing with this MPC protocols as technology. Um, so essentially, many things would have been possible. The most simple solution would just be check if the address, the encrypted address of some actor, that's encrypted in a transaction would be part of a blacklist essentially. That would be the most
Hmm.
simple approach, yeah. And then
Right.
traverse through the graph.
Yeah, that makes sense. A blacklist would most likely make sense. Yeah, I was asking because I know there are a few there are a few similar systems like that deployed on other chains, and I know that they have a certain degree of a failure rate, right? That they are prone to false
Yeah.
positives. For instance, if a bad actor was to send you ETH that they've taken through a money laundering, like a mixer or something, then your wallet, even though you've done nothing wrong, just purely having that ETH could flag your account as being
Yeah.
fraudulent or illicit.
Yeah. Um, and that's really why I think this approach just makes so much sense, because um, there can be a more sensible decision making process, because anyone would have been caught in this system, right? Because it happens after the fact, ex
Right.
post, you're able to decrypt. So yeah, that was really the idea. And then just really just every day working with this novel concept of encrypted state, and running computations over encrypted state, and being able to um, still reveal information, or yeah, some information about this data to the outside world. Yeah, really just made us realize that we need to make this a system that can be used both on the blockchain itself natively for
Right.
um, confidential on-chain use cases, but also for traditional enterprises to use, because combining this technology with distributed systems and blockchains makes it so much more powerful. Those paradigms we talked about earlier, right? Those
Mm.
new paradigms that arise from this combination of both technologies. So that was really an important realization for us, and made us so passionate about building this to large scale. And hence, we are also very happy to have such great investors on board, also believing in this vision, because um, it really allows to use the best aspects of blockchain technology, um, and build far better systems that wouldn't be possible without utilizing blockchains.
Right. Yeah. 100%. There's so much to gain by leveraging that technology. Okay. So obviously, this is still for you guys work in progress. You haven't deployed to the mainnet yet. That's still on your roadmap. But before we get into that, tell me a little bit about the specs. Right. It's a dedicated network. Have you done any testing of the throughput of TPS? And do you have any plans to connect to other chains? And if so, via what protocols are you planning to achieve that?
So right now we're starting to roll out the first round of private testnet. I can't give you a precise transactions per second, or in our case, CPS computations per second number. Um, what what's important is that our network really is um, chain agnostic to a certain degree. So um,
Right. That's
for the
cool.
start, we're looking at deploying on Solana, but um, there's no reason why Arcium shouldn't be available on all kinds of networks, right? And that's really the power of having this stateless confidential computing network. So we can access different blockchains, and we can use on-chain computation scheduling on those dedicated networks in order to be able to facilitate that. And there's no central state the entire network would rely on, to be written to. That's very powerful because if there's state that needs to be updated, this state lies on the dedicated blockchain network, and there's no overall slowdown, no performance penalty coming from that, right? If we were to support Ethereum mainnet, that wouldn't slow down any of the operations occurring on Solana mainnet. So I think that's important. And so step by step, we're gonna be expanding to different ecosystems as well, but in a sensible way, I guess. Um,
Right.
and what's important about the specs, I guess, really is that we under the hood allow for the usage of different kinds of backends. So if we have, for example, confidential on-chain applications for DeFi, that will most likely or should use a different backend in Arcium than if you're training an AI model in a
Right.
decentralized, federated
Just to
way.
clarify, what do you mean by backend in this context?
So MPC protocol.
Okay. So different encryption protocols.
Not necessarily encryption per se, but um, for example, number support. So if we are talking about those um, traditionally talking about those traditional on-chain operations, you will most likely not have this need for processing a lot of floating point operations, but that's very necessary if what you're trying to achieve is to trustlessly train a confidential machine learning model. And so there's different specializations, and depending on the need for the application that a developer is developing and deploying, a different backend is selected, and it's possible to switch between those.
Right, got you. Okay, that's very cool, and that's useful too because it keeps like overheads, performance overheads at a minimum there. So, what are your plans then regarding the developers and the businesses that are planning to use Arcium? How would one go about building something on Arcium? Do you support smart contracts? Do you support an API, or like what is this interaction between the infrastructure layer and the developer?
Yeah. So what's important to realize about the network itself is that the network really is a purely computational network. So
Okay.
what that means for the developer would be that you can't deploy a smart contract directly within Arcium. What you can do is you can tell the Arcium network, run this confidential computation for me, and it will very efficiently do so, and we'll be happy to do so, right? And so how can you build a confidential smart contract now? Well, it's different layers on the technology stack. And so on the most atomic layer, the network is, I don't know. I think you could call it a sort of um, distributed confidential operating system that those nodes are running, and that supports a specific set of atomic instructions, which again, depending on the backend, if you have those floating point operations, can be um, um, I mean, you could run logistical regression, or you could do some large matrix operations directly natively, like you would be communicating with a dedicated
Right.
um, GPU that has those instructions, but now it's sort of confidential. And so you have those atomic operations, and a developer could write a program, circuit sort of, that directly addresses those individual um, gates, those individual instructions, like you could write assembly code on your machine. So the most low-level code. So the developer could, in theory, add additional optimizations, but that's not something that we want the average developer to be required to do. And so we support a DSL language, so a domain-specific language. On top of that, that's this higher level language that's very familiar to use, and so the developer can just access all functions through that. Again, building confidential computations. And now one layer above that, the developer is able to write confidential smart contracts, because now this functionality gets integrated into a confidential smart contract SDK, which you can use within your smart contract. So for a developer, it's just about adding confidential functions to a smart contract, to an existing smart contract even. And the the core system that we're working with, and I mentioned it briefly earlier, is this MXE MPC execution environment. And within that environment, the developer can create persistent encrypted data objects and different functions like smart contract instructions that then get boiled down to those layers below, executed by the network and settled back. And that's how the developer can access Arcium. You can build an off-chain confidential application with Arcium,
Right.
or you
I
can
was
build
just
an
thinking
on-chain smart
you could
contract.
just call the functions from wherever you want. Really, you could even deploy your own blockchain on Cosmos or on Polkadot or whatever. So long as you have access to
Exactly.
that
Yeah.
low level information, you could just use the functions. That's cool. And you could also, so the plan is then to allow to allow building these encrypted or private smart contracts, if you will, on Solana. Is that what you mean when you say it's going to be deployed on Solana? You're meaning that there's going to be a library there that
Exactly.
people can
Yeah.
use, right? That's
Exactly.
very cool.
Yeah.
And it's probably just going to be like one function, right? Like compute this, and there'll
Yeah.
be the
So
output.
yeah. So I think the beauty of this system really also arises from not being forced to have everything be confidential, right?
Right.
Whatever has to be confidential now can be confidential, and what should be public can remain public. And so, with this setup, we make it very easy to switch between those two contexts, if you will. Yeah, and
Hmm.
so I think um, that's really what matters to developers, to be able to on their own define this should be public but this should be private, while at the same time not um, force them to be cryptographers, not force them to be
Right.
experts in the field, right? Because in the past it was really okay, I want privacy in my application, then I'm just gonna now become a zero knowledge proof developer, I guess, right? And so
Yeah.
with what we are trying to achieve, it's really with those MXEs, those autonomous executing machines that have this censorship resistance, that smart contracts can just call, that off-chain applications can just call, and make it as accessible as possible. Yeah, because that at the end of the day really is the deciding factor between users and enterprises and whatever using confidentiality or not at all.
Yeah, there's definitely tons of use cases there. So you've mentioned that you're in the process of launching the private, like a private launch for the testnet. Are people able to opt into that, or how would one go about engaging with the testnet at this stage? Could anyone start running a node if they wish?
Yes. So we we have different cohorts, if you will, that we are using for the testnet. I don't know how many cohorts in total we'll have, but um, the demand for those slots to be able to help us battle test the infrastructure and have access to the development tooling um, is insane, honestly, and yeah, that makes it very difficult. But we are super excited about that, and so we've just started with our first group of roughly a few hundred people, and um, many orders of magnitude above that wanted to get a chance to join in this round, but they'll have a chance to join in a future round. So. Um, it's been amazing to see the growth of that technology. I think within the last few months, our community on Discord alone has grown from, I don't know, 5,000 members to now close to 50,000. I think so. It's
Oh, wow.
insane numbers, and a lot of people wanting to get in and build completely different kinds of applications, various use cases. So um, I get messaged a lot about ideas people have that they want to realize, because now they understand with the tech that we are building, it's now possible to build these kinds of applications in a feasible way on the blockchain. So there's teams building on working on DeFi applications. There's DeepIn teams, there's AI teams, there's machine learning teams, um, there's healthcare teams. So it's really all use cases, and we're trying our best to onboard as many people as possible, but um, we'll do so in a sensible way in order to allow, um, I guess, good development progress to take place.
Yeah, then that makes sense. That's really good for the adoption, though. Congratulations. Um, what was I going to ask? I was going to ask about the right, the hardware required to run this. Do you need any specific hardware, or can you just download it and run it on your machine in most cases?
So that's an excellent question. By default, we don't force any hardware requirements. At the end of the day, how this network works is that um, the user um, could fully or um, um, yeah could essentially fully control who's part of a cluster for their virtual environment, and so um, they will pick nodes that they trust, and they will pick nodes that can facilitate their computations. But at the same time, um, you can use Arcium to also run permissioned clusters. I think that's important, right? So you can create a node and offer it for anyone to use. And we have this, again, with the collateral staking and slashing mechanism, there's also um, uh, this a design we currently have in our public docs with delegation mechanism, which allows for more fair distribution and more decentralization, and allowing smaller operators to increase their hardware capabilities. But it's possible to offer your computing power, if you will, for the public use with permissionless clusters, but the two of us could use our laptops and create a permissioned cluster and just run a computation um, collaboratively. That's an that's the secondary aspect, I guess. So it's really about allowing for autonomous execution environments, those MXEs in our network, where it's really just a replacement for a traditional centralized cloud server, I guess, right? VPS. So it's really just confidential operations with no middleman and no trust involved. At the same time, multi-party computations natively have the support for collaboration, right? So there's this native support of multiple parties computing a function over sensitive data, being able to gain new insights from that data without having to share a single bit of information with each other. And that's enormously powerful because it allows for, I think, best example would be in the medical space, allows for completely new intelligence, right? You can now, as a patient, you can now um, provide your data for a machine learning model training without having to risk your data, while at the same time getting those benefits from everyone doing this and running this computation, and then getting good models that allow for prediction of diseases, which otherwise wouldn't be possible because who would you trust your sensitive data with, right? So I think this enables, by doing more data protection, um, to get even more valuable insights. Yeah, in
Mm,
many domains.
right. Yeah. Yeah, for sure. So, 'cause you said you can run it on virtually any machine, but are the algorithms that are performing the computations over the encrypted data, are they better suited to run on a GPU or a CPU natively?
So the primary limiting factor really is network bandwidth.
Right.
That's
Okay.
the limiting factor for throughput for computations, because, as I said, for the computations there's still communication required at some point during a
Mm-hmm.
computation. So we think of network bandwidth to really be this limiting factor for throughput. At the same time, we make use of hardware acceleration to a certain degree with if you run your node with a GPU, it will definitely be more efficient. But it really depends on the use case that this specific node also is targeting again. So if we're speaking about AI use cases again, and that's why it's also so beautiful that this network has this notion of different backends, because um, you might not have a spec'd out graphics card, but that's not a problem because there's multiple backends that you can be running. So I think it's really what we're trying to do is to allow for as many different parties to run nodes as possible, because that fosters distribution and decentralization. And since computations occur in subsets, it's not a problem because individual slower players won't slow down the entire network. And then players can specialize. So node operators really can specialize on different kinds of applications to be facilitated.
Right. That's very cool. So when's the mainnet launch? When's it happening?
Yeah, um, great question. Um, Unfortunately, I don't have a great answer to that. Yeah, I should ask my developers that. So the team is very hard at work. We have an amazing team, full of hardworking engineers and researchers. So every day we're moving closer, but will still be a few working days until then, I guess.
Fair enough. Yeah, no, that's understandable. So you've got the private test nets now, which you said you're just onboarding people in batches, and then the next step is the public test net, right?
Yes.
And I
Yeah.
guess a certain
Exactly.
period of testing
Yeah.
and measuring, and then the mainnet launch.
Yeah. Exactly.
How about the node rewards? Uh, how do people get rewarded? Do they get like what's the reward mechanism there? I'm guessing that's a important incentive for
Yeah.
some.
Yeah. That's important. And for us, it's really important to essentially just facilitate this peer-to-peer infrastructure. So that
Hmm.
means you, as a developer, assigning a cluster this role of processing your confidential computations, creating this virtual environment, means that you, per computation, pay those nodes, and they equally get rewarded for that. And so there's no player in between. That's the basic mechanism. And of course, then based on network supply and demand, there's a priority fee mechanism. But on the most atomic level, it would really be um, pay per computation.
Okay, so there's basically your bandwidth dictates your rewards effectively if the bandwidth is your bottleneck.
Exactly. So it's really you, you as the node operator, um, um, yeah, setting the upper bound by your hardware, and then, of course, the mechanism is a bit more complex, but it circles around you unlocking your hardware, but with increased collateral then. Because there's an increased dependence on you not failing, right? If you're part then of more clusters, and so that ties into that as well.
That's cool. That's cool. Well, listen, I think you guys are building some amazing tech, and I would love to see it in action. And I'm gonna keep following along with the project's progress. And do give me a shout once it goes live, because I would love to see some of the use cases, or see how it works on the mainnet. Um, is there anything that you want to announce at this stage? Maybe anything you want to let people know? If there's devs that should be going to check out the website or the Twitter or anything like that.
Yeah, so as I said, we've started onboarding the small first very small batch into the private testnet, and so if you're interested to start working on building applications with Arcium, now is really the phase to start joining our developer community, because um, there's still with this private testnet, this process of going back and forth with developers and adapting the protocol, adding features, adding more features to the different backends, really depending on the use cases. So we really have this open community. Feel free to join us. We have a lot of community calls as well, where you can ask questions. So feel free to join the Arcium family.
Awesome. Listen, I think it's been great, and I will follow along with your guys' progress. Thank you, Yannick, for coming to the pod, and you're welcome anytime. I would love to have you again post launch, just to kind of discuss the use cases and your journey to mainnet.
Thank you so much, Andre. It was a pleasure.
Take care now. Bye, everyone.
All right. Take care. Bye.